Hi, good morning everyone. My name is Desmond, and today in this video, me and my colleague Kang are going to present about Haber process. So, Haber process is an industrial process that creates or to produce ammonia gas. So, before we enter to the Haber process, let us see and know what is ammonia. Please allow me to share my slides with you. So, what is ammonia? When you think about ammonia, usually we think about a colorless gas, and it is very smelly, which brings out that it is a highly irritating gas with pungent smell or suffocating odor. And it is very alkaline, as we know, since the alkalinic value, the pH value of it is very high, so it causes it to be very corrosive, as you can see here. But instead of all this, it is very widely used and it is very commonly produced in the industry. And it is naturally presented in our human bodies because it's very essential for us. For example, for the biological processes, it uses ammonia to be a precursor for the amino acid and also for the nucleotide synthesis. And in the environment, the ammonia is being used for the nitrogen cycle also. And we can see that everything revolves around ammonia, and it is a very important substance to be used. So, what are the uses of ammonia? We can see here there are 6 main different places where we use ammonia. The industry, agriculture, household, food and beverage, water purification, and underground resources. Let's go there one by one. In the industry, it acts as a source of nitrogen. So we use it to produce plastics, explosives, textiles, pesticides, and also dyes. So when it comes to rubber, it acts as a premature coagulation agent. So it prevents the premature coagulation of rubber so that we can know and we can estimate when does the rubber is needed to be coagulated. And for the leather, we make it as a curing agent. So it makes the leather more soft and it makes it more firm to be processed in the later on processes. Moving on, in the agriculture sector, about 80% of the nitrogen or the ammonia is being used in the fertilizer, livestock feeds, and also crop protection. So we know that ammonia is a very important source for the fertilizer. It helps the plants to grow. And in the food, in the livestock feed, it acts as a protein enhancer. So it gives them extra protein for the food for them to intake, especially like cows, sheep, which we usually eat their meat. So for the crops, we can make it as a protection for pre-harvest cotton or antifungal agent for certain fruits, or even it can act as a preservative for the storage of high moisture corn. When we came to the household, about 5% of the produced ammonia is being used in the household area to be used as stain removal agent. And even in the industrial, we use about 25% of our produced ammonia also in the removing of stains. So this is because ammonia is very corrosive and it helps to clean up all these things. A good example which we see every day would be this, or bleach or Clorox in the common name. In the food and beverage sector, it acts as a refrigerator gas. So it cools down the atmosphere gas or the environment so that it gives it a cool temperature. So it helps keeping your food cool and it also helps to cooling some agent, and especially in some very big companies or big industry, they also use ammonia gases as their cooling agent. In the water purification process, we also use ammonia to clean the waste, to clean all the substances that are needed to be cleaned off in the water so that we could intake or we could get clean water to be used. For the underground resources, usually we could use it to extract metal or treat metal from these iron cores or other metal cores, ores, and we could also protect the equipment by neutralizing the acid constituents. Example, like the petroleum field. In the petroleum plant, they usually use the machine to get petroleum from the oil field. But in order to maintain it, in order to maintain this expensive accessory or this expensive equipment, we must use the ammonia to protect it, like to neutralize the acid when you are getting the things. So, how can we produce this useful product? My colleague JK will be helping us to discuss further about Haber process and the science behind it.
Thank you, Desmond. I will now continue the presentations and explain more about the Haber process. Allow me to share the screen. Well, the answer for this question is definitely through Haber process. Haber process is first invented by Fritz Haber and Karl Bosch. This gives it an alternative name as Haber-Bosch process. It is an artificial nitrogen fixation process, and it allows the conversion of atmospheric nitrogen to ammonia by reacting it with hydrogen in the presence of iron catalyst. This picture indicates the flow of the Haber process. First, hydrogen and nitrogen will pass through the compressor, which lower the pressure, and then be sent to the reactor in the presence of catalyst to let the reaction happen to produce ammonia. The ammonia will then be passed to the condenser to be liquefied for further use. The unused hydrogen and nitrogen will be recycled back to the reactor for the next reaction. Thus, we now have a rough image of what is Haber process. We will now go deep into the condition used to maximize the synthesis of ammonia. The temperature should be 400 degrees Celsius to 450 degrees Celsius. The pressure will be 200 atm. The volume will be low volume. The concentration should be high concentrations of nitrogen and hydrogen with a ratio of 1 to 3. Catalyst is also present in this process, and the catalyst used will be iron or ruthenium as the second generation catalyst. Before discussing why are these conditions is used, now let us look into the concept of equilibrium constant, which will be used in the explanations later. Equilibrium is achieved when the rate of the forward reactions equals to the rate of the reverse reaction. This equilibrium constant, Kc, can help us to understand whether the reaction tends to have higher concentrations of product or reactants at equilibrium. The Kc is calculated using the concentrations of reactants and products in equilibrium state. Kp is another form of equilibrium constant which calculated from the partial pressures of a reaction equation. The P of Kp stands for pressure and the C of Kc stands for concentration. There's an example of expression of Kp for the reactions of 2 nitrogen dioxide react to form 1 mole of dinitrogen tetraoxide. There's another form of constant, it's called There's another concept of reaction coefficient, QC. It is expressed similarly as Kc, with the difference is the concentration used in QC not necessarily has to be in equilibrium state. Well, with the value of Kc and Qc, the direction of net reaction can be predicted, and also we can determine whether the system is in equilibrium or not. Well, how do we determine the direction? Well, how do we determine the direction of net reactions and the system is in equilibrium or not? It's through this relationship of Kc and Qc. If the value of Qc equal to the value of Kc, then the system is said to be in equilibrium and there's no net reaction. If the value of Qc is larger than the value of Kc, then the system has not achieved equilibrium yet, and there's a net reverse reaction, and this goes vice versa. Well, the Haber process uses Le Chatelier's principles as a reference to maximize the production of ammonia, as this principle can predict the effect of a change of condition on chemical equilibria. The principle states that when any system in equilibrium is subjected to conditional changes, the system will react such that by shifting the positions of equilibrium to minimize the effect of the altered conditions. Well, the main 4 conditional changes are temperature, concentration, pressure, and volume. Firstly, we'll look into temperature. Consider the following reaction. The reaction is an exothermic reaction that liberates heat energy. When temperature increases, or as the reaction goes by, it will liberate heat. The reverse reaction is favored as it is an endothermic reaction that absorbs heat. When the temperature decreases, or we manually remove the heat, the forward reaction is favored as it liberates more heat. Thus, in order to increase the yield of ammonia, low temperature is used in the process of synthesizing ammonia according to Le Chatelier's principle. The next factor will be pressure. The change of pressure can be done by increasing or decreasing the volume. This factor will only affect the gaseous equilibrium system with unequal stoichiometry of reactants and product. The following examples are the reactions that will not be affected by these factors, which is 1 mole of hydrogen react with 1 mole of hydrogen, react with 1 mole of chlorine gas to form 2 mole of hydrochloride gas. On the other hand, for the reaction of Haber process, it will be affected by this factor. It is that when the pressure is increased or we decrease the volume, the forward reaction is favored to reduce the stress. This is because the mole of gases product of forward reaction is only 2 mole of gases, which is smaller compared to the reactants, which is 4 mole. Thus, in order to balance the increase of pressure, the reaction will favor the forward reactions. And also, when the pressure is reduced or increase the volume, the reverse reactions is favored to increase the stress. Therefore, high pressures should be used to increase the amount of ammonia produced, as it favors the forward reactions according to Le Chatelier's principle. Well, for the volume factors, the changes of volume is related to pressure, which increasing the volume causes the pressure to decrease and vice versa. Hence, lower volume is preferred as it can increase the pressure of the system, result in higher amount of ammonia produced. The last factor will be the concentration. The following reaction will be the reaction of Haber process and the expression of QC. When increasing the concentrations of the reactant, which is the nitrogen and hydrogen, the value of QC will be lower than the value of Kc, resulting in a net forward reaction. If we increase the concentration of the product, which is the ammonia, the QC will be larger than the Kc, thus result in a net reverse reaction. Therefore, high concentrations of nitrogen and hydrogen should be added to produce more ammonia. Well, after the discussions of the condition used according to Le Chatelier's principle, there's some difference between the condition used in the industry There's a difference between the condition used by the industry and the conditions suggested by the Le Chatelier's principle. Well, I will explain it now. For the temperature, according to Le Chatelier's principle, it suggests that low temperature should be used, which is different from the condition used in the industry, which is 400 degrees Celsius to 450 degrees Celsius. The reason behind this is because low temperature will slow down the rate of reaction, and it will take a much longer time to produce ammonia. On the other hand, if high temperature is used, it can speed up the reaction, and it will take a much shorter time to produce ammonia. Although the ammonia produced will be lower in percentage of U, comparatively, it can get more yield of ammonia in a fixed period using high temperature compared to low temperature. Thus, high temperature is preferred by the industry rather than low temperature. Well, the second will be pressure and volume. Low volume and high pressure is recommended to increase the production of ammonia. Well, the condition used by the industry is low volume and a moderate pressure, which is 200 atm. Well, why the industry use a moderate pressure rather than a high pressure is because they have to consider the economic factor, as very high pressures are very expensive on two counts. First, extremely strong pipes and containment vessels have to be built to withstand the pressure. This will increase the capital cost of the plant. Furthermore, the maintenance fee of the plant for high pressure will be very high. Thus, the compromise pressure will be 200 atm, which is high enough to maximize the production of ammonia. This same goes for volume, that we will be using lower volume compared to higher volume that can increase the pressure. Lastly will be the concentration. It was suggested that to use a higher concentration of nitrogen and hydrogen in a ratio of 1:3. Well, why don't the industry only increase one of the reactants? Well, this is because if you only increase one of the concentrations of the reactant, it will cause the reactants with lesser concentrations becoming the limiting factors. Examples like if they only increase the concentration of hydrogen, there will be no enough nitrogen to react with hydrogen. Thus, the excess hydrogen or the unreacted hydrogen will become a waste of money to the industry. Thus, therefore, the ratio of 1:3 is very important. Moreover, the catalyst is used in this process to speed up the reaction in a way that it will not affect the positions of equilibrium. If the catalyst is absent in the Haber process, the reaction will be so slow that virtually no reaction will happen in any sensible time. And that's all for me. I would like to share a video of the Haber process.
You have likely produced ammonia in the laboratory from the thermal decomposition of ammonium chloride or from the reaction of ammonium and hydroxide ions. Have you ever wondered how ammonia is produced on an industrial scale? In this lesson, we will learn about the Haber process to produce ammonia, developed during World War I by Fritz Haber and Carl Bosch. For their efforts and contributions to developing large-scale industrial processes, they were awarded with Nobel Prizes in chemistry. The Haber process is the industrial process for the manufacture of ammonia from hydrogen and nitrogen. Hydrogen is obtained from the reaction of methane and steam, producing carbon monoxide as a byproduct. The hydrogen produced from this reaction also reacts with oxygen from air, producing water and leaving nitrogen behind. Recall that air is 77% nitrogen. These gases are then compressed and delivered to the reactor, where ammonia is produced. These gases are then cooled down and ammonia is liquefied, ready to be tapped off. Unused hydrogen and nitrogen are recycled back to the reactor. Let's revisit this reaction again. Note that this is a reversible reaction and that the forward reaction is exothermic. The Haber process uses Le Chatelier's principle to maximize ammonia production while keeping operating and production costs in mind. Le Chatelier's principle tells us that increasing pressure will favor the side with fewer moles. For our case, the production of ammonia. It would make sense to conduct the reaction at a very high pressure, but we must also remember that it is expensive to build and operate a plant that can withstand such high pressures. Therefore, a compromise pressure of 200 atmospheres is used. Let's keep Le Chatelier's principle in mind. What do you think is the best temperature conditions to maximize ammonia production? Please pause the video to think about this and resume once you are ready. Since the forward reaction is exothermic, it would make sense to conduct this reaction at a low temperature. The compromise temperature is 400 to 450 degrees Celsius, which is not exactly low, but not too high. If a low temperature were used, the rate of reaction would be very slow, though the exothermic reaction would be favored. It would actually take a long time for equilibrium to be reached, so a compromise temperature of 400 to 450 degrees Celsius ensures that the reaction proceeds with sufficient yield. The yield of this process is 10 to 20%. Remember from the introduction that unused gases are recycled, so no reactants are wasted. As well, an iron catalyst is used in this process. The presence of the catalyst does not affect the position of equilibrium, but increases the rate at which equilibrium is reached. In conclusion, the Haber process is the industrial process to produce ammonia from hydrogen and nitrogen. It is conducted at 400 to 450 degrees Celsius and at 200 atmospheres in the presence of an iron catalyst. These are compromise conditions in order to maximize ammonia production and economic profit.
Thank you, JK, for your explanation. So now, let us do a little revision by having an example. From here, let's try to find the Kc and Kp of the Haber process. From what we know from JK, the chemical equation of the Haber process is 1 nitrogen react with 3 mole of hydrogen provides 2 mole of ammonia. So in the Kc, it will be the product of the reactants to the power of the coefficients over the product of the products to the power of the coefficient. So we can see from here, the Kc of it will be this. The concentration of ammonia to the power of its coefficient, which is 2, we see here the 2 mole, over nitrogen multiply hydrogen to the power of its coefficient 3. In this case, the product or the Kp of the Haber process will be almost the same as Kc, which just we change the concentration into the partial pressure of the gas, since ammonia, hydrogen, and nitrogen are gases all in the normal condition or in the standard condition. So let us find the relationship between Kc and Kp. We can find the relationship by using the ideal gas equation. PV equals to nRT, which R is our constant, our gas constant, and T is in the absolute temperature. N is the number of mole, P is the volume, and V is the volume, and P will be the pressure. So let us see the overall equation. And by moving the total volume to the right-hand side, when number of mole divided by volume, we can get a concentration. So let's see, P equals to molar RT. So by having this equation, we'll sub into these 3 other gases and we'll get these 3 equations. So from here, we can get the relationship of partial pressure and concentration. So while substituting all this partial pressure into the Kp equation, and we can get this combined equation. So after deriving this, after simplifying it, we'll get this part. So from here, you can see this equation is the same as Kc, shown as here. Which means that this brings out the equation that combines Kp and Kc together. So we'll see that Kp equals to Kc multiplied by RT to the power of -2. For a -2, we will say it is the difference of n, which is the difference of coefficients shown here. So it is the end product minus the reactants. Okay, the number of mole of the end products minus the number of mole of reactants. Okay, so the gas constant in overall is 0.02806 liter atm per mole Kelvin. Okay, now let us try. In one of the Haber experiments, 0.025 mole of hydrogen gas and 0.010 mole of nitrogen gas are combined in a 2-liter vessel at 472 degrees Celsius. The mixture is allowed to come to an equilibrium, and the concentration at equilibrium of ammonia is observed to be 3.18 times 10 to the power of -5 molar. So let us calculate the Kc and Kp for the Haber reaction at this temperature. Okay, let us try this question. So from here, from the question, we can know that the initial concentration of hydrogen and nitrogen and also ammonia. So ammonia is given directly in the question, 3.18 times 10 to the power of -5 molar. While for the concentration of hydrogen, we must take the number of mole divided by the volume, just like what we showed just now, N over V. So we'll get the number of mole. So 0.025 divided by 2, we'll get 0.0125 molar, while nitrogen is 0.10 divided by 2, we get 0.005 molar. So let us find the equilibrium of the Haber process of this question. So the initial molar will be 0.005, 0.0125, and in the beginning, we don't have any ammonia. Because at equilibrium, we'll get 3.18 times 10 to the power of -5. So let us count back the process. So 1 mole of nitrogen will get 2 mole of ammonia. In order to get back the number of nitrogen used, we must convert the number of mole. So 1 mole of nitrogen provides 2 mole of ammonia. So in order to take back how many nitrogen are used, we must divide the number of ammonia get by 2, right? Okay, so from here, 1 over 2 times 3.18 times 10 to the power -5. We get 4.9841 times 10 to the power -3. So this is the same for the hydrogen gas, but in this case, it's 3 to 2. So we need to multiply our 3.18 times 10 to the power -5 by 3 over 2. And this is the answer we get. So in equilibrium, we need to find the Kc of it. So by using the same formula, substitute inside the concentration of each gas, and we'll get 0.10508. So now let us move on to find the Kp of it. Since the partial pressure of each gas is not given, so we can use the relationship between Kc and Kp to find the value of Kp. So the equation has been derived at here. If you are still not sure, please rewind back and refer to it. So by having this, we can get 0.10508, which is our Kc, R, 0.08206, and T is the absolute temperature. So we must add 273 into the given temperature, which is 472, sorry, and power it to the power of -2. So in the end, we'll get the answer of 2.8115 times 10 to the power -5. So in the end, this is our KC and this is our KP. So our video will end here, and I hope you guys can know more about what is ammonia, what is the Haber process, Le Chatelier's principle, and how do you use it in your daily life, or even how do you calculate it when you are in the industry. Hope you enjoyed the video, and please remember to keep safe during this crisis time. Thank you.